Okay, so firstly, I'd just like to reaffirm the comments that were made previously, speaking as I think someone who's come a long way to attend this meeting. It's been completely worth it, and so I'd again like to thank the Cambridge organisers, both for inviting me and also for organising a really fantastic discussion of the current status of our thinking about the universe. The second thing I need to do is to apparently, I thought coming to Cambridge, I thought putting a little French tag in my title would be transparent to all involved. But a number of people have asked me what my talk is about, or what my slide is about. And so, so despite the fact that I assumed that this would be okay, I will begin by providing a quick lesson. It's apparently a shortening of a phrase in French that translates as "the more things changes, the more they stay the same." And I guess there has been a sense that our understanding of inflation hasn't changed dramatically in the wake of Planck, and there was this hope that Planck would see a dramatic change in our grip on the early universe. I won't try and pronounce it because I attended a school in New Zealand that was modelled on a very traditional British style of school, little hats and blazers and caning, and they imported teachers from England because those were where the best teachers came from. And the man who taught me French had been in the British Army, and he was fond of addressing boys as if they were on a parade ground. And we couldn't understand him when he spoke English because he spoke with this very thick upper-class English accent, and we couldn't tell a difference when he spoke French. So, so he's very much of the "if you say it loud, the foreigners will understand" school of French pronunciation. So I can read French, but I unfortunately will not try to speak it in the company of people who grew up on the continent of Europe. So that ends that part of my talk. So now I want to just, this needs no, the Planck satellite needs no introduction. And I guess the other thing to say is to salute the people who worked on this. This is the second smarmy part of my talk. But I mean, it really is one of the most profound achievements of modern science to have measured this light that has been traveling to us for 13.8 minus 380,000, 13.8 billion years minus 380,000. And to have extracted, 2,000 numbers that tell us something about the global properties of the universe from the multiple expansion is really quite remarkable. And it's been fantastic as a theorist who's closely associated with the analysis of this data or the understanding of what this data can do, but not involved with the experiment itself. It's really been a fascinating process to watch. On the other hand, I think what that's actually done for the theoretical community is we've been looking forward to this for so long. We kind of believed that somehow we would wake up the day after the Planck satellite announced its results and would go outside and the sky would be a different color, that the world would change completely. But it turns out that the only thing that changed the color of the sky was that Planck people chose a different color map for their CMB map relative to the WMAP one. But our immediate understanding of the universe didn't change profoundly. And I actually, just out of curiosity, I looked up the number of papers on spires that use the phrase Planck mission, Planck spacecraft, or Planck satellite somewhere in the opening of the paper. And you can see that people have been writing papers about this at a pretty steady rate since the beginning of the 21st century. And it kicks up a little bit with the launch. You see the spike with the data release in March, and then you see that things have continued. So we have been anticipating this day for a very, very long time. And we are, I think, theorists kind of risk feeling as if they're children that have gone and unwrapped all of their presents, holiday presents, and they've found, not exactly the thing that they were hoping to find. There is no non-Gaussianity at the moment. We haven't found features. We haven't found, some radical extension of the lambda CDM paradigm that we'd grown used to. So I think it's actually worth reminding ourselves exactly what it is that we have as cosmologists, and let's quickly review what it was that we already knew. What? Well, I'll take it any time you want. My birthday is in November. So I think one of the key things is that the lambda CDM cosmology, we heard a lot at the beginning of the conference about the experiments that have been done at the LHC. And again, the same story is told there. The discovery of the Higgs was a discovery, but in some sense it was confirmatory rather than a revolution in our understanding of particle physics. It would have been a bigger surprise if we'd found strong evidence for physics beyond the standard model, or if no Higgs had shown up at the LHC at all. And it's, in some sense, I think that we're in the same position with regard to lambda CDM cosmology. One of the things I would want to say about lambda CDM was to remind us is that there is very strong evidence for beyond the standard model physics in the way that we look at the universe. So, people at the LHC say we haven't seen anything beyond the standard model. It turns out people who do cosmology have seen things beyond the standard model for many years. And so let's just remind us what these numbers mean. So we know we have Hubble's constant, And this is a number that we're never going to be able to determine kind of a priori, because it's simply a number that tells us when we happen to look at the particular scenario that we're looking at. So this tells us that the fundamental parameters in the model are a function of time, and when we choose to carry out the observation, whether it's at 13.8 or 14.8 billion years, is going to change the values of the parameters that we measure. On the other hand, there are three parameters that, that are only two of them if we have a prior that the model is flat, but the baryon fraction, the cosmological constant, and the amount of dark matter in the universe. All of those things relate to physics that are outside of the standard model and are presumably telling us something about particle physics. The problem is we don't necessarily know what that something is. Looking at inflation, we measured the primordial power spectrum in terms of the amplitude and in terms of the spectral index. And it's worth stressing that these aren't fundamental parameters. These are purely empirical parameters that relate to some convenient characterization of the power spectrum. They're not numbers that show up directly in gut scale or stringy physics. They're simply convenient ways of characterizing an unknown function, but they're related somehow to physics at the gut or the string scale, potentially. And finally, we have the reionization physics. And those, in principle, in many cases, I think the reionization physics is something we could compute a priori if we were only smart enough. It doesn't necessarily relate to new physics, but it does relate to physics that we can't easily quantify. So the glass half full approach to this would be to say that Planck has confirmed our fundamental understanding of the universe. And this should be good news. This is the way that science is supposed to work. We have this deep understanding of the universe. It's surprising in many ways in terms of the dark sector. But it's telling us that, in fact, despite this surprising and apparently counterintuitive version of the universe that we've come to have, that we can greatly increase our ability to measure the universe without necessarily seeing that we have to add any new parameters. So it tells us that the model we had actually has a surprising amount of explanatory power. We had a model, it survived, and the parameter volume contracted. So in some sense, this is a successful prediction. The problem is that doesn't tell us as cosmologists what it is that we need to do next. The glass half empty version of this story is that there were many things that we were hoping to see and we got nothing. So we didn't see any non-Gaussianity, we haven't seen any evidence for tensors, and we haven't seen any new evidence for features, either in terms of large-scale anisotropies on the sky or in terms of features in the power spectrum of the CMB. There's also the questions around late-time physics, whether it's neutrinos or non-standard dark matter. I'm going to focus more closely on the early universe here. So I think one of the things that's worth doing is actually, it's more than 30 years ago that inflation was described in detail. And so I think it's worth pausing and reflecting, what is it that we should expect from an inflationary model? And the first question is to ask a really deep question, what is inflation itself? And so the standard textbook description is to say that inflation is accelerated expansion. It's a phase in the early universe during which the second derivative of the scale factor in Einstein gravity is positive. But you could be a little bit more subtle in this distinction and in this definition, and you could say that in fact what inflation is it's a period during which the co-moving horizon size is contracting. And so that is what you need, in fact, to set up the apparently acausal structure that we see in the present universe, where patches of the universe that apparently haven't been able to communicate with each other were in causal contact at some point in the past. So you can take some region that's well correlated, you cause the co-moving horizon to contract, and then you have the universe that we're living in. And that can, in fact, be achieved in other ways. It can be achieved through ekpyrosis, or these brain world models. It can also be achieved, if you want, by having a very large speed of light in the primordial universe, which then allows you to correlate things in a causal fashion, but on scales that are much larger than the one we currently live in. So if you adopted that definition of inflation, and to some extent it's a historical accident that our first working model of inflation was also one that had directly accelerated expansion, then you would have a somewhat different view of inflation. And particularly, I think, if things had worked differently, the thing that we would have seen as being the fundamental prediction of inflation is that the perturbations that seed the formation of large-scale structure in the universe existed at recombination. So this isn't a particularly new result, but what it does is it tells you that if the perturbations are there when the universe is ionized, you're going to have a different polarization, because the way that electrons will scatter, if the perturbations are there to produce a potential wells that they're moving inside of at recombination, will be different if relative to a universe in which the perturbations were laid down when the universe was electrically neutral. And so this correlation was observed by WMAP in the early part of this century. And as far as I know, it was actually first worked out by Spergel and Zaldariaga in 1997. I asked Dave for the reference on this. Matthias may want to, is there any prior art on this? You don't think so? So, if inflation had been invented by people who are astrophysicists, whose primary job was to think about the CMB, it's highly likely that this correlation would have been worked out in the 80s, and it would have been presented to us as the key prediction of inflation. This would have been the smoking gun of a universe in which the co-moving horizon size was decreasing as a function of time. So we've observed this by WMAP observed this, but the thing that we've been waiting for is the observation of tensor modes, which is often presented to us in terms of, as being the canonical thing that inflation gives you, because the models of inflation that people were primarily used to in the 1980s were models of inflation that have large values of the scalar field, large energy, and therefore naturally produce a substantial tensor contribution to the primordial perturbation spectrum. So that's as a matter of kind of historical curiosity in some sense, but the key thing to remember is that inflation has already made very, very non-trivial predictions that have been verified with an enormous amount of confidence by existing microwave background measurements, and I'm sure will be further confirmed by Planck when its polarization maps become available. So the next thing that people have talked about a lot is the non-Gaussianity. And so again, it's worth reflecting on what is actually natural for what is our natural expectation for the non-Gaussianity in the context of inflation. And to some extent, I think a large FNL is in some sense a street light, because we've all looked under it, but our keys may well be somewhere else. In some sense, it's analogous to supersymmetry in the context of the standard model. Thousands and thousands of papers have been written on supersymmetry, but there's no compulsion for the universe to either be supersymmetric or to be supersymmetric in a way that we can hope to measure at the LHC. So all of the different models of inflation that people have proposed, it's very natural to see something that gives you an approximately Harrison-Zeldovich spectrum. But on the other hand, we see that the value of the non-Gaussianity that you compute in the standard FNL parameter covers many, many orders of magnitude. So clearly this is a quantity that has huge discriminatory power, because you have a quantity that can vary by at least a range of 100 relative to NS, which NS minus 1, which varies by just a factor of a few between models. And so it's clear that the non-Gaussianity is going to be very good at choosing between models. On the other hand, again, I want to salute the people who have performed this analysis, because the ability to constrain multiple multiple different styles of non-Gaussianity in a single calculation is something that has rendered what would otherwise be a completely intractable analysis tractable. So it's a beautiful piece of work that's gone into the Planck analysis. And so the problem is, from the point of view of providing surprises, if you look at simple inflationary models, they tend to predict that the amount of primordial non-Gaussianity you expect to see is proportional to the first slow roll parameter epsilon, and that by definition is a quantity that's much less than 1. Interactions in the early universe will typically give you FNL of order 1, even if it's not primordial, and as a matter of cosmic variance, a value of FNL of on the order of 1 or order of a few is the limit for a measurement that's based on a CMB. So from this perspective, any measurement of a primordial non-Gaussianity would have involved a model that was in some way non-minimal. So I don't think it should come as a huge surprise to us that that Planck has returned a null result for a primordial non-Gaussianity. There was no particular reason to expect that it would that FNL was going to be 10 or some greater number for some easily observable triangle. On the other hand, FNL tells us how it was that the universe went about shrinking the co-moving horizon, because the interactions between modes depend much more sensitively on the inflationary mechanism itself than the mechanism that produces the modes in the first place. So non-Gaussianity is a null result. It tells us that inflation is in some sense closer to a minimal scenario than we might previously have thought or hoped. So the next thing to look at is the perturbations. And I think this is now a pretty familiar plot for people who are working in this area. It's one that versions of it were produced by WMAP, and now we're seeing this is the version from the Planck paper. And so the standard thing to do is to take the predictions of different inflationary models and lay them down on this plane and relative to the tensor amplitude and to the primordial tilt. And so the volume allowed in here has shrunk substantially, but it hasn't yet shrunk to the point where you're going to be able to rule out a large number of inflationary models that were viable when you only looked at the WMAP9 data. A key thing that comes out of this is a question of whether or not a simple model of inflation is also in some sense unnatural when you look at it from the perspective of particle theory. And so Cliff Burgess said exactly the same thing in his talk earlier this week. And so one of the things that I took away from this week, in fact, was how optimistic the CMB community is about their ability to measure very, very sensitive measurements of the primordial tensor ratio based on observations that are carried out from the ground, which are both going to happen over a shorter time scale and also with smaller expenditure of money relative to the launch of a subsequent satellite to Planck. So I think this is a huge deal, because if you can lower the tensor scalar ratio by a factor of 10 relative to where we are at the moment, then it has a huge discriminatory power in terms of your ability to rule out a large and significant chunk of the inflationary model space. And so I think if you want to have there's two versions of simple that coexist in the literature. And so from the point of view of people who are doing cosmology, simple often refers to simply the algebraic complexity of the potential. And so the two models that you can really write down with a single term, without any additional folderol, is you need to have a model in which the inflationary phase itself produces the perturbations that you see. You need to have a model in which inflation comes to an end. And you need to have a model in which the bottom of the inflationary potential is arranged such that it doesn't, that it produces a minimum where the potential has a value of 0. And so the two simplest examples that we can think where this happens are the case of the m squared phi squared potential and the lambda phi fourth potential. So one of those models has already been ruled out, famously ruled out by even the first release of the WMAP data. And the other one is actually looking quite ill. If you go back to the previous, slide, the m squared phi squared is really starting to sit there at the sort of 2 sigma level relative to the WMAP data. So both of these models are looking ill, and so their sense is what do we learn about that as theorists? And so what we might be learning is, in fact, that the universe is really Wilsonian in some sense, that it really cares about, if you simply write down a naive potential where the value of the scalar field becomes larger than the Planck mass, then you really better provide a detailed mechanism in which that can happen without turning on a whole bunch of extra interactions that are going to generically ruin that for you. So there's many, many ways to define this simplicity, even ignoring effective field theory. And so just again, this is an argument that's going on for a long time. Just want to mention these two calculations. But it looks like if the Planck allowed region of that parameter plane simply contracts around its central value, then we're going to be living fairly soon in a region where you've ruled out the simplest models of inflation, and you're going to be looking at models of inflation that may be more algebraically complex in terms of the ways in which you might want to define that, but on the other hand may make more sense from the point of view of whether or not you have control over the higher order operators that appear in an effective field theory description of your fundamental theory. So another way to look at this is, there's really 3 different jobs, as I said previously, there's 3 different jobs that the inflationary potential has to do. It has to provide the inflationary phase, and if you have a period of inflation that's driven by a very flat potential, then what that tells you is it tells you that dv d phi, the epsilon parameter, which controls the tensor to scalar ratio in simple slow roll inflation, it's telling you that that is a very small number. And so if that's a very small number, it's telling you that the inflaton potential isn't going to be changing very much as you move by a small distance in phi. And that means that that the scalar index is going to be dominated by the second order term, the eta term in terms of the standard slow roll and expansion. So if you want inflation to come to an end, you have to put some sort of curvature in the potential, and you can either do that gently by putting in the next higher order term, or you can arrange for the potential to have a sharp transition where you're rolling towards the top of the Grand Canyon, and then there's a very sharp transition that causes you to fall off the inflationary attractor, a so-called waterfall transition. And then on top of that, you have to add another piece to the potential to see that once you've made the potential steep, you can then make it shallow again, so that inflation will come to an end around a stable minimum of the potential. So I think it's not unreasonable to say that there would be a model of inflation that has three parameters in order to provide each of these features is probably not, should not be regarded as excessively tuned, because there are 3 separate things that the inflaton potential has to do, and it's just a happy coincidence that in the case of m squared phi squared or lambda phi fourth inflation, that you can do all of those things with a single potential. So if I wanted to define simplicity in terms of low hour inflation, then I would be happy to see a potential that had 3 adjustable parameters in it. the next thing we can talk about is we can talk about the presence of features, or rather the apparent absence of features in the microwave background. And so this is something that I have been thinking about myself a fair bit this year, because one of the things that we wanted to do in the warm-up to Planck, which I did with Haranya Pires and Raphael Flauger, was to actually look at the predictions for a monodromy potential and to look at that in the WMAP9 data before the Planck data entered the public domain. And so we're looking at a modulated potential here. I'm just realizing I may in fact be using a less ambitious version of this. So when in the final result, I think this this potential should actually be more, should be visibly modulated, but still modulated at a level that's small relative to the overall amplitude of the CLs. And so this particular scenario is coming from a monodromy inflation model. And so there's no need for a feature in the potential, and that's true both from the theoretical perspective. There's no reason why you should violate the smoothness of, the smooth and kind of gradual evolution of the inflationary universe. There's no compelling reason to do that. And there's also nothing in the data that makes that compulsory. But it's also true that features arise in many models, and I think it's arguably more common than to expect something to happen in explicit stringy constructions where you've taken an inflationary trajectory and you've somehow folded it into a more complex potential. Because as as the inflaton field evolves its way through that potential, particularly with substantial values of R of the tensor to scalar ratio, then I think you have to do some. There has to be some complex construction that causes that to happen, which then opens the possibility that this complexity will manifest itself in the power spectrum. And the other thing to be aware, of course, is if you had any data set in which you had no apparent 2.5 sigma violations of smoothness when you've got thousands of numbers in your data set, you expect that there will always be 2 and a bit sigma hints that there's something funny going on in your data set, and the absence of those would actually cause you more concern than trying to continually sort of organizing ambulance chasing missions to explain the presence of these apparent anomalies. So having said that, I want to focus on 2 examples. The first is this monodromy potential, and so in a very restricted form it can be written down in the shape. I noticed that I haven't included the term that would cause this potential to be stable around its minimum. And this was discussed in some detail by Raphael in a talk in one of the parallel sessions. The key thing is we analyzed it both in WMAP9 and Planck, and so the WMAP9 analysis was done with Haranya, and then Raphael took the lead in analyzing the Planck data in some detail. And the question we had is we found, in fact, a fairly interesting signal in the Planck and the WMAP9 data, which we then had to ask whether or not we could recover that in the Planck data. The key thing about this model, rather than going into the nitty-gritty construction of this model, is that there are 2 clocks in this model. So there's a standard clock that controls the overall height of the inflationary potential as it evolves, which is what eventually causes inflation to come to an end. But because this particular model, the inflaton potential, has been wrapped around a cycle in the compact space that's associated with string theory, the wrapping direction also introduces a second period, time dependence in this model. And the time dependence of the wrapping in this scenario can be much more rapid than the time dependence of the overall inflationary model itself. So as well as having this slow, gradual decay of the potential as you move towards the origin, you also have this very rapid modulation, which is represented by this cosine term here. And so this shows itself up in a modulated spectrum. And when we looked at the WMAP9 data, we found this very interesting modulated posterior for this f parameter, which controls the speed of the modulation. And you can see that there's a very strong and pronounced spike around a particular value of that parameter. Again, the amplitude of the modulation term, again, because you have the strong spike, it also has it has a significant value. When this parameter b is 0, there's no modulation. So one might reasonably be excited about that. And when you look at the change in the likelihood from the WMAP9 data, the change in the log likelihood is on the order of 19. But this was not fully recovered in Planck. There's a lot more to do on this because, in principle, the WMAP9 data and the Planck data should coincide with each other when you look at a restricted sky map. So it's not yet clear why it is that when you restrict the WMAP data, the Planck data to look like WMAP, you don't see the same thing. Raphael had some comments on exactly what the resolution might be of this in his talk, so you should check with him for more details about that. But it is true that in the Planck data you see an improved fit for similar parameters. It's just that the improvement in the likelihood is less dramatic. So it's worth saying that the fitting here is hard work. The difference, the results depend sensitively on the form of the modulation that you assume. And so in particular, you might worry that if there really is a real signal in the sky and you're fitting some template to that signal and it's not quite the same as the real signal, what will happen is there'll be some region of L space, for instance, in which you're fitting the signal well and you'll see an improvement in the likelihood. But if there's a slight mismatch between your template and the signal, there'll be another region, in fact, where you're out of phase, and you'll actually wind up beating against the signal that you've got, and the two things will cancel out. So in a scenario where there really is some signal there, thank you, then you can in fact expect that there will be very, very sharp peaks in your likelihood, which makes this a much more challenging analysis than the sort of thing you might have done with more smoothly varying parameters. The second thing to say, which I think is important and a more generic lesson that can be learned from this, is that the delta, if you just use a delta chi-squared statistic, there are three parameters in a modulation. It's phase, its frequency, and its amplitude. And so if you take the usual delta, I'm going to fit to noise, so I expect an improvement in delta chi-squared of 1 per degree of freedom. Then it turns out that if you actually do simulations of this, so this is a result that Raphael obtained, it turns out that if you do simulations of this, you in fact see a typical delta chi-squared on the order of 10. And so the reason for this is you're no longer in the in the regime where you can kind of conveniently just expand the top of the likelihood surface in some sort of minimal Taylor series expansion. And so what that means is that if you can easily get a delta chi-squared of 10 from this sort of scenario, which you might naively think was a fairly big improvement in your fit, but is in fact entirely what you would expect from fitting to noise. So whenever you're doing this kind of analysis of features in the primordial power spectrum, it's worth bearing in mind that what you see and what you analyze, you have to be very, very careful with your statistics. The next thing that people have been talking about a lot is the case of large angle anomalies. And so this is a nice example of the Planck sky map provided to us by the New York Times. And there's also a fine example here of, you can just see it in the newspaper actually. I think I've found the right one. There's Stephen, here we are at Cambridge, and Stephen Hawking's initials are again clearly visible in the microwave sky. So what this really does is it firstly, there are no new news on large anisotropies in Planck, because Planck these correspond to large scales, and they were already measured to cosmic variance and doubling that. So polarization will make a difference. That's not yet available. There may also be interesting things you can do with cross correlations. But in general, we're not going to learn anything about very large anisotropies in the microwave background that we didn't already know before we started. The next thing to bear in mind is that there's a huge number of possible anomalies that you could imagine looking for in the CMB. So you might not just find, no one yet has gone and found Ed Witten's initials in the CMB. So maybe that's telling you something about string theory. No one's found Isaac Newton's initials in the CMB, so maybe that's telling you something about gravity. No one's found Einstein's initials in the CMB. We've only found one. So we can imagine, at least 26 squared combinations of initials that we could have gone looking for in the CMB, and we've found just one of them. So I think we have to be very careful of the fact that we're performing an a posteriori analysis here, and we're focusing only on the possible anomalies that appear to be interesting. And so I talked to some statisticians at Auckland about this recently. They asked me to give a talk because I was using the phrase Bayesian in the title of my talk. And they said, oh, well, you should have worked all this out before you looked at the sky. In other words, you should have a hypothesis before you go and gather your data. And I said, thanks for that advice. It's come a little late, and we don't really have the luxury of doing that. And so the corollary of that is we have to be very, very careful when we perform this analysis, because it's very easy for our monkey brains to pick out things that are shiny. In this context, I've been looking with my postdoc at Auckland, Gregor Aslani, and we've been looking at various ways in which you might drill down on this. And in particular, as you know, there's a huge list of CMB anomalies. There's the axis of evil, there's a cold spot, there's a parity violation, which means that different CL, odd CLs have more power, I think it is, than even CLs at low L. There's a lack of power in the sky at low L. There's this hemispherical anomaly. If you look at the Planck paper, they're looking at p-values relative to random realizations of the sky. And so the question is, there's nothing, all they're doing is taking a realization of the sky and asking whether you would see this particular anomaly if you performed 100 or 1,000 realizations. And the question is, because there's no causal mechanism that's being provided in terms of this analysis, the question we wanted to ask would be, if one anomaly is real, which of the other anomalies would we also expect to see? You can't answer that question unless you have some mechanism that tells you how those anomalies were put there in the first place. And what we tried to do was to say, well, let's imagine we have a mechanism for anomaly, let's have a prior. And a particular example we looked at was to take a large, one K mode in the early universe, one particular mode, and to imagine that had been artificially amplified for some reason. So this was a large planar anomaly, and it turns out you can, when you project this planar anomaly onto the CMB, expand it in terms of YLMs, it turns out that it will generate your parity anomaly for you depending on your alignment. So it can make some of the CLs large and some of the CLs small in the way that people have talked about. It can also, for some configurations, generate part of the multipole alignment. It won't necessarily generate all of it, but can generate a piece of it. And so you can look at your best fit anomaly in terms of taking this particular anomaly, working out what your best fit is, and then you can ask which of the anomalies that it could have produced it actually produces. And in this particular case, we can do a good job of predicting the parity anomaly, or producing the parity anomaly, and not so good job of producing the axis of evil, even though in principle we could have produced chunks of both of them. This obviously needs a lot more work. In particular, it depends now, of course, on the model that you're assuming for the early universe when you do this work, and it also assumes on the particular form of the anomaly that you have chosen. So there's the question is, what is my basis of anomalies that I might inject into the early universe at large scales in order to perform this calculation? But at least if you have a particular model, then you can form some assessment of the physical likelihood of any particular scenario that you're injecting, because you now have some causal mechanism, and it can also potentially, the third thing it can do is it can produce potential anomalies that you haven't observed in the microwave background, and the absence of those potential anomalies again is going to give you additional constraining power relative to simply fitting to the sky maps itself. So the question is, what next? I want to ask this question, finally grapple with the question of what's going to happen next in cosmology. And so what I have to put on this map is I put two hypothetical constraints on NS and R. I just punch them in using the graphics tool in Keynote. And both of these things are where we might imagine ourselves being a few years from now. If we can shrink the constraints on NS by a large amount, or we can either measure tentatively the primordial tensor amplitude, or alternatively that we can rule it out with some precision. And so the key thing to draw from this is that the inflationary predictions have a theoretical uncertainty. And it's worth reflecting on where those come from. All of the inflationary models that the Planck team shows, they show them as a line rather than a point in the NS&R plane. And this difference is related to reheating physics in the primordial dark age. So if we have gut scale inflation, we could conceivably have reheated the universe to a temperature of maybe 10 to the 15 or maybe even 10 to the 16 GeV. Or we may not reheat the universe until we had a temperature of a few hundred MeV, because the thing we know we have to do is to produce Big Bang nucleosynthesis and the neutrino background. So the universe could have been matter-dominated that time, or something even more exotic might have happened. But modes re-entered the horizon more slowly in a matter-dominated universe than they do in a universe that's radiation-dominated. And that means that you need to have fewer E-foldings of inflation in a model where you've had a long delayed period of, where the universe remains matter-dominated for a long period after inflation. So this particular equation here is from a paper that I wrote with Harania Pires, where we tried to work out the so-called matching equation in some detail. We had the number of neutrino species in and so forth as well. But the key thing to take away is, if you imagine gut scale inflation and it remains matter-dominated down to the TeV scale, you get from that the logarithm of the scale factor that you need differs by about 10 relative to what you would expect if you reheated efficiently. And that means you need 45 and not 55 E-folds of inflation. We know that dn d log k in typical models of inflation is a few times 10 to the minus 4. And so that means that the theory error that we expect to see is on the order of as a few times 10 to the minus 3. That's exactly what we see. That's exactly the length of these lines. And so if we go back to the inflationary, the best fit inflationary results that we see that currently Planck has measured NS to within about a factor of 3, to a point where we're not only going to constrain an inflationary model itself, but we're also going to constrain the combination of the inflationary model and the post-inflationary expansion history of the universe. And so when that happens, we're going to be able to, competing models of inflation disagree dramatically about what the primordial dark age should have done. SUSY scenarios, for instance, are rife with moduli. versus models that have rapid thermalization. So we'll be able to tell a difference between those two things. And so even if nothing else happens, even if we add no new parameters to the to the standard inflation cosmological parameter set, I think we are going to be able to learn about the primordial dark age. And this is going to be key for model building, because once you've built an inflationary model inside of a particular version of high energy physics, then you're also going to be able to say something about reheating in that scenario. It's also worth pointing out that dark matter and baryogenesis, dark matter ogenesis and baryogenesis have to take place in the post-inflationary universe. I have a couple of slides on the parametric resonance and the production of gravitational waves in the early universe from oscillons. I'm just going to skip those. I'll put them online. Let's just go past these. This is actually just mentioned, this is work that I did with Ed Copeland and his student recently. So we've taken these oscillon scenarios that you can, again, nonlinear dynamics can happen in the very early universe, produces a matter-dominated phase in a way that's completely invisible if you look at the Lagrangian itself, but that you get coming out naturally just from the fact that you can have complicated dynamics in your in the underlying power spectrum, and the underlying post-inflationary oscillations lead to the formation of these long-lived scalar field excitations and a corresponding generation of gravitational waves in a way that was discussed in some detail again in the parallel sessions. So to move to my summary before I get shown the final warning to the zero. So this is, I only had 35 minutes. You said I had 40. So this, I think the summary is that the world is going to change for early universe cosmologists. And the question I think we're all expecting, that Planck would somehow lead to a first order, a strong first order phase transition in our understanding of cosmology. The phase transition may be weakly first or maybe first order, but super cooled, and that there's some large surprise that's yet to come. Or it may change slowly, but I think eventually it's going to change substantially, even if we never wind up extending lambda CDM. The second thing that we're learning is that apparently simple models of inflation have rich phenomenology. And working out the phenomenology is going to keep the community busy. Again, even if we don't, the standard lambda CDM parameter set stays fixed as a function of time. And finally, what we're learning is that simple models of inflation, particularly if you define simplicity in maybe a more sensitive way rather than simply sort of as a matter of historical accident, I think it's fair to say that simple models of inflation are in remarkably good shape at this point. And so that then the sort of basic expectations that were formed around inflation in terms of it being something that correlates the universe on apparently super horizon scales, when the universe is very dense and very hot. Though that's a scenario that has been strongly confirmed by experiment, and something that appears to now be a part of the standard cosmological furniture, which is not going to go away. So I think that's where I want to end, and hopefully I'm not going to see the -5. Thank you.
Okay, we're kind of running a bit late, so let's just have one question. Oh, George, you've asked lots of questions. Andre, just pick somebody. If they want. I'm trying to look for some. Okay. Oh, go on then.
So, Richard, if you go back to the beginning where you showed the residuals relative to a monodromy model, right?
Yes.
Okay.
I think this may actually be the wrong plot.
Yeah. So, yeah. I know, but it's good enough. So the thing is that what kills you with Planck is that third burst.
Right.
Okay. Because the first two, the data are highly cosmic variance. The cosmic variance error is big, and so you can pick out something statistically from WMAP. But with Planck, that burst at 800 to 1,000, that produces large visible residuals.
Right.
Okay, and it's just excluded easily from Planck data. So that's why the WMAP parameters don't fit with Planck. That's the primary reason. The second thing is that I've spent a lot of time looking at these models and doing extensions which allow your phase factor to vary with wave number because you know just a slight mismatch can screw
precisely
things up.
the thing we were talking
And there is just nothing. Right? No evidence for anything.
That doesn't surprise me to hear it. I think the one thing that I think still is to be worked out is why it is that we didn't recover. And I think that, I mean, Raphael has some very good ideas as to why this is. Why it is that even in the range where you expect Planck and WMAP to agree with each other, you still don't see an exact recovery of the WMAP9 results. And so I think that.
That will be you can't match experiments because of the noise levels and stuff.
No, and also because of the sky cuts.
So and a slight mismatch, just a slight mismatch, will give you very different results.
Okay, no, I'm not. I mean, my personal feeling is that, you know, it remains to be seen. I mean, my feeling is that, you know, the natural expectation is that, you know, as I said, is that there's no reason to expect that features exist in a model. This is an example of a search for some. The other thing I would say about this one in particular, again, if you went to Raphael's talk, the region of parameter space in which I mean, the nice thing about this analysis is we have a very specific scenario that, you know, rather than a generalized modulation which would lead to a look elsewhere effect. So, you know, we've made one prediction and we've gone and looked at one model. The particular region of parameter space where you find this very strong fit is in a region where the underlying physics may not be perfectly controlled. So you would actually potentially expect to see some change to this. I mean, both of those things I think need to be sorted out before you can be completely, you know, it would be really nice to know where it is that this additional noise, that this additional power comes from in WMAP. And I don't think that question's yet been fully answered. I mean, there still remains, you know, some mismatch between, I mean, it's the same points I think were made by David Spergel and his you know, so I think, you know, a year from now, I imagine we will understand this more clearly. You know, well, maybe you understand it more clearly because you've seen more of the Planck data than we have. But
Okay, let's thank Richard again.
Yeah.